In the media, you often see experts warning about how everything is going to end. They usually mean war, political revolutions, economic crises. But on this rare occasion, we'll speak to someone who wrote the book about the actual end of everything, as in the whole universe, how it'll happen and when it'll happen, according to the best science available to us. Before you panic, it's probably going to be a few billion years from now. So we're good, for the moment at least, for the duration of this interview. Up next, renowned astrophysicist Dr. Katie Mack joins us to talk about space-time, dark matter, black holes, and how we can actually know such things about our universe spanning these billions of years from its very beginning to its very end. This is the InnerView. And Dr. Katie Mack is also the Hawking Chair in Cosmology at the Perimeter Institute. Really great to have you on the program. How are you doing?
I'm good. How are you doing?
Very, very good. Very excited to talk to you. And also, I was very thrilled to learn that Hozier had a lyric about you as well. As Mack explained, there'll be darkness again. I mean, forget all your achievements, forget the PhD, forget all the studies. I mean, that's a fantastic artist, and you've been immortalized. It's probably better than having a star named after you. How did that make you feel?
It's definitely an honor. I'm a huge fan of his music, and it's a lovely song, and it's all about the end of everything, so it works out well.
Okay, so we've got your book in the video wall, The End of Everything, Astrophysically Speaking. It came out a couple years ago. How has the book done, and has anything surprised you in terms of the response to the book?
I think it's done well. You know, I think a lot of people have read it, have enjoyed it. I think the thing that surprised me the most was that a lot of people told me that it made them feel hopeful, that it was comforting to read about, you know, the ultimate destruction of all reality. There's something about thinking about these really big questions, you know, thinking about this long-term, you know, ultimate stuff that puts everything in perspective in your own life.
Something that's interesting probably is that with the Big Bang, it folds in a lot more, I don't know, religion, philosophy, and divisiveness over how things began and who began it and when it began. Whereas with the end, not so much, because every belief system almost accepts that there's an ultimate, I don't know, collapse of things, you know. So it's a less political thing in some weird way. Do you find that as well?
Yeah, it's interesting. You know, I think that a lot of belief systems have some kind of ending, some kind of big finale. The difference, I suppose, between a lot of those ideas and the kind of scientific view is that in most of the religious philosophical ideas, you have something that kind of gives everything meaning after the fact. You know, there's an ultimate reward, or there's some way in which everything is set right. Whereas in the cosmological view, you don't really get that. So you have to figure out what meaning is in the present rather than having it depend on something that's going to happen after everything is over.
Right. What does, because you're an astrophysicist, but you're also a theoretical cosmologist, and I don't think the two are exactly the same thing. Maybe there's a lot of overlap. What does a theoretical cosmologist do?
Well, so cosmology is the study of the universe as a whole. So the study of the cosmos, the beginning, the end, the evolution of the cosmos, what the universe is made of, what the laws of physics mean and how they work in our universe. So a theoretical cosmologist is somebody who tries to work out how all those things fit together, what the evolution of the universe was, what the early universe was like, using the tools of mathematics and then comparing that to data potentially, but really trying to build a mathematical model of how the universe works.
Right. And you're a theoretical cosmologist and not a cosmologist because the Perimeter Institute doesn't have the budget to send you to Andromeda and stuff like that, right? So, yeah.
So there are experimental and observational cosmologists. It's just the difference is that they touch data a lot more often than I do.
Yeah, I mean,
I mostly just work with the equations.
poor attempt at humor from me. But okay, so looking at the end of everything, I know that the best available science says that there's an end to life on Earth in roughly 5 billion years from now, give or take, I don't know, a few hundred million.
It could be. It's more likely a bit sooner because the sun will destroy the Earth in somewhere between 1 and 5 billion years, but the Earth will become too hot due to the expansion of the sun, to the brightening of the sun before that. So maybe about 1 billion years before the oceans boil away and life is probably over on Earth.
Right. And there was a fascinating piece that you wrote about how the observation of the light spectra from a white dwarf, which was, well, it was an example of what our sun will become. And you correct me at any point here because you're the expert.
No, that's all right, yeah.
And you were looking at the different wavelengths and the spectrums of light, and you found that the star basically consumed its planets that were in its orbit. And that is a sort of living or dead example of what is going to become of us. Tell us a bit more of that.
Yeah, it's fascinating. It's something that I don't work on personally, but I was reading about it. So our sun, when it dies, it'll puff up into a red giant, and then it'll blow off the outer layers and become what's called a white dwarf, which is a very, very dense, very hot object that'll just kind of fade over billions and billions of years. And so we know what's going to happen to our sun, and we see other white dwarf stars out there in the universe, remnants of other stars like our sun. And we've seen examples of white dwarfs that have clues in the spectrum of the light that there are heavy elements on the surface of these stars. And those heavy elements really could only have come from planets. And so we have this evidence that these stars have basically eaten their own planets. The planets have been destroyed by the stars, and the debris of the planets is kind of mixed into the star now. And when I first started studying that, reading about that, it was a fascinating moment of thinking about, that's what's going to be left of the Earth, where the clues about the existence of the Earth will be just a little bit of dirt in the spectrum of a white dwarf star. And, so we're looking at these stars, and that could be the remains of great civilizations. We don't know.
My daughter asked me about why we're sort of looking into a time machine, why we're looking into the past. And I muddled through it, and my answer was a little bit verbose and choppy in trying to explain how long it takes the light to reach us and stuff. So maybe as the astrophysicist, in a more succinct way, tell me why what we're looking at through our telescopes or with the naked eye is often something that's already happened a long, long time ago.
Yeah, so anytime you look at something, the way that you see it is that the light from that object is coming to your eye. Usually it's reflected light, if from right now the sunlight is reflecting off of my face and going to the camera, and, it travels through that. But anytime you look at something, you're looking at the light coming from that thing. And light is not instantaneous. It takes some time to travel. So whenever you look at something, you're seeing a version of it that's as old as, the light took that time to get to you, right? So if you look at something that is just a few feet away, you're looking at a few nanoseconds ago. It didn't take very long. But if you look at the sun, you're looking at 8 minutes ago. If you look at another star, you might be looking at hundreds of years ago. If you look at another galaxy, you're looking at billions of years ago, because the light took billions of years to get to you from that other galaxy. And so every time we look at anything, we're looking in the past. But when we look out into space, we're looking in the deep ancient past, and we can learn about the early stages of our universe that way.
Okay. I'm glad I'm going to clip that up and send it to her, because it's a better answer than I could give. Okay, so we know how the Earth would become uninhabitable, and our sun would, even before it swallows us up, the oceans will be burned, the atmosphere will be gone, right?
Yeah.
Now, what's the best theory for how everything ends, how the whole universe ends, which is what your book is about?
Right. So the kind of consensus view, the most likely view based on the current data, is that we end with something called a heat death. Now, when I say heat death, that makes it sound hot. It's really a very cold process. What happens is that everything kind of decays, the universe gets bigger and bigger, and things get more and more spread out. So the universe is expanding, galaxies are getting farther apart, all the galaxies are kind of moving away from each other on the long distances. And so the universe is becoming more and more empty and colder as all the energy spreads out. And everything's kind of decaying, and it decays into this kind of waste heat, like just like inefficiency, it's just disorder. And at some point, the universe gets so big and spread out, and things have decayed so much that you reach this kind of maximum disorder state. Everything is just completely destroyed, decayed, and that's called the heat death, the ultimate heat death of the universe. And that is it's also sometimes called the big freeze, because everything kind of just fades away and becomes cold and dark and empty and sort of uninteresting. Nothing ever happens again. So that's what we think is the most likely end at this point.
And when's that going to happen?
Very long time from now. It's one of those things where we don't have words for the amount of time. You can go trillions and trillions and trillions of years, but it's longer than that.
I want to ask you, why does it seem as if these titans like Einstein and Stephen Hawking, why does it seem that every renewed discovery, every addition, every little additional nugget that is found seems to validate what they've said, what they've found? What makes them so special? Do we underestimate just how special they were in helping demystify our understanding of the universe?
So I think that in the case of Einstein, he was a crucial figure in developing some of the really important pieces of modern physics today. Relativity, special relativity, which talks about how time and space are connected to each other, especially when you're moving really quickly. And then general relativity, which is about how gravity works in our universe. Those models have held up, and we're sort of surprised by that, because we've been testing, especially general relativity, for years and years and years, and trying to find where it might break. And we think it has to at some point, because it doesn't seem to agree very well with quantum mechanics, which has also been extremely successful. So I think part of it is that Einstein just found this really great model for how the universe works, and for whatever reason, we haven't found the edges of that. But we think probably there is some point at which it probably breaks down. We're not certain, but maybe, at least if we want to find a way to connect it to quantum mechanics. It could be that quantum mechanics is the thing that breaks down. We don't know. So it's one of these things where it was an idea that worked really well. And, Einstein wasn't alone in his work. There were a lot of people working on a lot of these concepts, and the same with Hawking. He came up with a lot of really important things in physics. Some of them haven't been tested, things like Hawking radiation, this way that a black hole might evaporate at the end of its life. We don't have evidence for that. We think it probably happens, but we're still studying it. So there's a lot of stuff that's kind of, these big ideas kind of capture the public imagination, and they're really important in our modern physics, but we're always testing. We're always trying to find, where it might break down. We never assume that somebody is correct about everything forever.
Yeah, there's a guy called Donald Hoffman, and I remember he said that at 10 to the minus 33, I mean, he didn't say it for the first time, but he was explaining that at 10 to the minus 33 at the sort of microscopic or what was quantum level, then space-time breaks down. But what I find as a layman, then you have this space that, I don't know, scammers rush into then to say that, well, nothing is real, nothing means anything, nothing Einstein said means anything. Everything is just, I don't know, a figment of your imagination. You construct your own reality, and so on and so again, when I was looking at one of your interviews, one of the algorithmic ads that popped up was one of those Mind Valley scammers coming up and saying, quantum jumping, you can escape your reality.
Yeah.
So, okay, Does it frustrate you that you have the real meaning of something like quantum and then the woo-woo meaning of quantum that a lot of people get seduced by?
Yeah, it is frustrating, you know, and I'm always trying to communicate that, you know, I think part of the problem is quantum mechanics is something that is very, very counterintuitive. There are things that happen on the quantum scale that just do not seem to make sense with the way that we think of how things work in our everyday lives. But it's not arbitrary, you know. Quantum mechanics is a science that is governed by extremely precise, complex equations. It's extremely mathematically tested. Like we've never found anything that doesn't agree with our models of how things work on the quantum scale. We have something called the Standard Model of Particle Physics that it was developed in kind of the 70s, and there's like one or two places where there might be some issues with it, but it's basically passed every test we've thrown at it. You know, we've got these incredibly sophisticated machines like the Large Hadron Collider testing every piece of it. We've got numbers that we know to, you know, 8 or 9 decimal places because the calculations are so precise. So there's really not a lot of wiggle room. There is inherent randomness in certain parts of quantum mechanics, but not places where you can just say, oh, we don't know anything, let's just assume that anything can happen. But I do think that this idea that quantum mechanics can give you special freedom to manipulate reality, I think that comes from a fundamental misunderstanding where people think that because quantum mechanics is counterintuitive, that means it's arbitrary, and it's really, really not.
Is this an exciting time for you? It's an exciting time for me in the sense that not only do I get to watch Cosmos, read Carl Sagan, watch Neil deGrasse Tyson, Brian Cox, the English, not the Scottish, not the Succession guy, but the other one. I mean, I love the Succession guy, but the other one as well. Yourself, it's wonderful for someone like myself to be able to learn from astrophysicists like you, Brian Greene, physicist as well. Is it as exciting for you to be able to share this knowledge with the mainstream?
Oh, absolutely. There's so many exciting things happening in physics and astronomy right now. You know, things from like the new observations that we can make, like with the James Webb Space Telescope, of the you know, earliest galaxies in the universe. We're starting to see glimpses of those. And then some of the new discoveries in physics, like gravitational waves. You know, we can detect the ripples in space-time as black holes are colliding in other galaxies. Just being able to say that is amazing, right? Just that we can see the universe in that way, to that precision. Things that are happening billions of light years from here, and we can learn about how space-time itself works and is altered and bent and manipulated by the movement of giant black holes. Like that's amazing that we can do that. There are just so many things. We can look at the cosmic microwave background, which is the kind of first light of the universe, the last light from the Big Bang itself, and we can learn about the very beginning of the cosmos, and we can make inferences about how the universe is going to end. All of these things are incredible to me, and I love sharing the information that we're getting and this perspective we have on the universe, the way that we're filling in this cosmic story. It's so much fun for me.
And amid all of this, there's this invisible force keeping everything together called dark matter. What is dark matter? Explain it to me explain it to me like I'm an idiot, and don't assume that I'm not an idiot, but please explain this to me.
So yeah, dark matter is my main area of study in my day-to-day research. It is some kind of invisible stuff that seems to be what holds galaxies together. So our galaxy is made of stars and gas and dust and black holes and all those kinds of things, but it's all kind of embedded in a clump of invisible matter. And that sounds far-fetched, right? It sounds weird, but there's a lot of things that we can't see that we know are there through indirect means. I mean, even just when you're walking down the street, if you feel a little cold on one side and you see the leaves moving, you know there's some wind. You can't see the wind, but you see all these indirect things that tell you that the wind is there. And it's kind of similar with dark matter. We know that galaxies are rotating faster than they should be. There must be something holding all that stuff in so it doesn't fly off into space. We can see that space bends in ways that we don't expect. So there must be some invisible matter bending the space. That's something that goes back to Einstein's picture of how gravity works. There are other indirect clues about how dark matter is there, things that all kind of add up to the same picture, that there's got to be some kind of matter, some kind of stuff that has gravity that we can't see, doesn't interact with light, can pass right through other kinds of matter, but is apparently the most important kind of matter in the universe. Something like 85% of the matter in the universe seems to be this invisible stuff. And it's probably just a kind of particle that we haven't been able to detect yet. And we're trying to get indirect clues about what it might be. But it seems to be the dominant kind of matter in the universe. And so what I'm trying to do is study, see how we can figure that out, how we can figure out what dark matter is, how it might have been interacting with the first galaxies in the universe, and what kinds of particle physics might have been occurring at that time that could give us clues about that. So it's an exciting topic because there are just so many places to look for dark matter because it's so important in our universe.
Yeah, I see equations over your shoulder in the background. Could you give me an example on any specific day of how you would go about trying to solve that riddle or that mystery of dark matter? What would you use? What would you be looking at? What would you be writing down?
Yeah, so my main thing right now is trying to figure out, so dark matter might be a kind of particle that when it comes into contact with others of its own kind, it can annihilate into particles that we can see. So maybe, we can't see the dark matter itself, but maybe it can interact and annihilate and become particles we do see. And if that's the case, then that should have been happening even when the first galaxies were forming. And so part of my project right now is to calculate, if that were happening, how were those particles that were created interacting with the gas in which the first galaxies were forming, and then how would that change the properties of those galaxies? And so I'm working with a team of students and postdoctoral researchers to put together a big sort of simulation code that can work out how those interactions happened, how the galaxies would be affected, and then what we would see with telescopes in the future when we're trying to figure out what was happening with those early galaxies. And so the idea is to first calculate with computers what the changes would be to what we expect, and then give that to the observers and say, what do you see? Do you see this or do you see something else? And that will give us some clues about whether the dark matter was doing this annihilation or not.
So the idea is the Big Bang happened at a sort of heavily concentrated point, and everything has been expansion since then, and evolution and change and all of that, the universe expanding, right? And I mean, we come from the guts of exploded stars as well, all the elements and so on, things coalescing with gravity. I mean, and you can you can correct me at any point here. The idea is so something small explodes into something bigger and expands and changes. Yes? No?
So not necessarily something small. So the universe was smaller in the past in the sense that it's getting bigger now. It's expanding. It's been expanding from the beginning, but it might have always been large.
Right.
So there's this weird thing where you can have a singularity, which is what people think of as like an infinitesimal point, but it can be a spatially extended singularity, which means that it could be everything's extremely dense, but also still very large.
Right.
And so the universe might have always been large. It might have always been infinite in size. There's this weird thing that can happen where you can be large and infinite and still expanding. So we know the universe was extremely dense in the beginning, but we don't know if it was ever like a point, and we don't think it ever was.
Yeah. Okay.
But yeah, it was really dense, really hot. Everything was kind of closer together, and things have been expanding and changing. And yeah, and it's evolving. And that's something that is a key point, I think, in what I try to communicate about the universe, is that it's very different than it was, and it's going to be very different in the future. The universe was very hot and very dense, and everything was, kind of this hot roiling plasma, and then it expanded and cooled, and stars formed, and then those formed heavy elements, and then that allowed for planets to form and life to form. And then in the future, the galaxies are going to get farther and farther apart, and that process will slow down. There won't be more stars forming. There won't be more planets forming. Everything's going to kind of cool and die off probably. I mean, there are other possibilities for the end of the universe, but that's the way it's looking.
So 2 final questions, and if you can
Okay.
answer them very briefly. So
Sure.
is your hypothesis that dark matter was constant, its nature was constant throughout all of this change, or that it also changed? That's first
That's
question.
a great question. So it depends on the model of dark matter that you're working on. I have some of my students have worked on models where dark matter was kind of something different early on and changed in the very early universe. But the sort of usual models are that dark matter was something that was born in the fires of the Big Bang, just like everything else. And it's just been, it's been spreading out, but it's been there since the beginning. And as, galaxies form, dark matter is the part of what's clumping together when those galaxies form and the stars form. So it's not evenly distributed through the universe, but it has been part of the universe all along.
Interesting. Okay, final question. In Interstellar, Cooper, the Matthew McConaughey character, when he goes into the black hole, how is he still in his human form? Why isn't he torn to shreds?
Right. So that could be a very long conversation.
Okay, no, 10-second answer. Are they wrong?
In general, it's a really bad idea to go into a black hole.
Right.
You will get torn apart and you will die. So don't do that. There was a special kind of model of a black hole that the writers of that movie were working with that may or may not really work out in real life. So don't try it at home.
Okay. Kip Thorne, as far as I remember. Yeah. Fascinating.
Yeah, he wrote a very nice book called The Science of Interstellar that you can read about.
Okay, Dr. Katie Mack, it's been a pleasure talking to you. Thank you so much.
Thank you very much.
Take care.